This is Functional Thin Films Lab, Department of Chemical and Biomolecular Engineering of KAIST. Professor SungGap is a principal investigator of FTFL and leading researcher in the field of ICVD process in Republic of Korea. Our lab is conducting research based on polymer thin films using initiated chemical vapor deposition process. In ICVD process, vaporized monomer and initiator flow into a chamber where they contact resistively heated filaments. The initiator breaks down into radicals by heated filament at the top of the chamber, and a free radical polymerization begins at the substrate surface due to the low temperature of the substrate. Our lab utilizes polymer thin films and applies them to various research fields. ICVD process has various advantages compared to liquid phase process. Because it is a solvent-free, no byproduct and room temperature process, damage-free polymerization is possible, and the inherently conformal nature of CVD allows us to produce a variety of structures. In addition, copolymer with various compositions can be fabricated regardless of miscibility, and it allows the polymer to be introduced onto various substrate materials. The ICVD system can be utilized in various applications. At first, we will introduce about nano-adhesive. We can fabricate various types of nano-adhesive layers, such as sub-minusculable adhesive, pressure-sensitive adhesive layer, and stretchable adhesive layer, and showed strong adhesion between many soft substrates like Ecoflex, Sylbion, and PDMS. Surface modification via ICVD process is also a major topic of our lab. It can control hydrophobicity by depositing thin film onto fabric and sponge, and can also enhance the stability of lithium-sulfur battery separator by amine-based polymer film. Moreover, it can be used as a reflow blocking layer while block polymer is under annealing process by using thermal stable monomer as DVB. The ICVD is a vapor phase process. Homogeneous mixing is possible regardless of miscibility of reactant. It is possible to control the surface energy and mechanical characteristics by finely controlling the composition of the two monomers, which are not miscible in liquid phase. In addition, polymers with high refractive index and transparency can be synthesized using element sulfur, which has poor miscibility with organic solvent in liquid phase. The ICVD system is also adapted to the field of electronic devices. Typically, polymer thin films deposited by using ICVD process have been utilized as a dielectric layer for TFT devices. Basically, due to the advantages of the ICVD process, such as high purity, low surface roughness, and easy thickness control, the fabricated dielectric film shows superior electrical performances. Through various studies, we engineered various properties of dielectric materials such as K-value, modulus, charge trapping properties by designing the polymer functionality and chain structure, and we applied them to develop various electronic devices. First, insulating films are used to design logic circuits. Through the thickness control and patterning, multi-stage logic circuits with various structures and electrical characteristics have been realized. In recent, a flexible ternary circuit with low power operation has been demonstrated through the ICVD process. In addition, the ICVD dielectric film is utilized to develop memory devices. The ICVD process is effective to fabricate low voltage operation devices by thinning the dielectric layer, and it is possible to diversify the memory characteristics by tuning the polymer functionality. Recently, the development of various types of memory devices is conducted, and applying them as neuromorphic devices is mainly progressed. Also, our lab utilizes polymer thin film as various means in cell culture system via ICVD process. We have developed several thin film cell culture platforms using the ICVD process, which has the advantages of vapor phase process. By controlling the surface free energy of By modulation of copolymer composition, we developed a cell shift technology that can control the cell-substrate adhesion. It was also used for long-term culture of primary neuron cells using a biomimetic polymer. The cell culture surface using the ICVD process was also used for spheroids researches. We figured out the interaction between the surface adhesive protein and cancer spheroid by studying the changes of the adhesion state according to the surface energy of the polymer thin film. Also, we confirmed the expression of extracellular matrix increased in MSC spheroid on the surface of the polymer film. Using ICVD-based polymers, molecular diagnosis has been improved to be easily and conveniently performed. We are developing diagnostic methods that can detect various pathogens such as coronavirus and influenza virus, food poisoning bacteria, and cancer with high sensitivity and specificity. We are also conducting research to develop antibacterial and antiviral surfaces and apply them to face masks and intraocular lenses. In summary, this laboratory is contributing to various research fields using the ICVD, which can be divided into 4 major fields. Up to date, the various studies using ICVD have been steadily published in many good journals as follows. And finally, these are the recent pictures of our lab. We are enjoying various exciting activities all together, such as picnic, summer and winter retreats, graduation ceremonies, and etc. Thank you for your listening.